In this section, we will cover two major processes. Fused deposition modeling is the first one, also known as fused filament fabrication. Here we will go through a general overview of the process, pluses and minuses related to the process, certain applications, and examples of vendors that offer machines for this and materials for this process. Let's take a look at the basic FDM process.
Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual-heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint.
More details of this excerpt video providing an overview into the function of the FDM process can be watched on YouTube at the link provided over here. Moving forward, some of the advantages and disadvantages of FDM include that you have properties that are decent. You can make durable parts. You can make fully functional components, and the parts can be post-processed to improve surface finish, appearance. One of the issues really is the anisotropy in the Z direction. That is a feature of the part. We saw a little bit of that when we covered mechanical properties towards the end of lecture 2. Because of the layer by layer approach, you end up having a step structure on surfaces that needs to get rid of. Fine details are impossible to be realized because you are working with a 1 millimeter to 3 millimeter diameter filament, and so that limits the surface resolution, feature resolution that you can get. FDM applications are wide. You can make prototypes, you can make support parts, you can make few limited edition parts. There has been an explosion of interest in 3D printing thanks to this method. Protopaster is one type of a vendor for FDM materials, offering many niche materials. ColorFab is another one that offers a wide range of materials. In addition to these examples, you have a number of other players as well, because the initial patents have disappeared for many of these. MakerBot is the most common, widely recognized name, but you have Maker Gear and a whole host of other offerings in the market these days. The second method that we'll be looking at is selective laser sintering, commonly known by a number of different techniques. If it's powders based on polymers, it's SLS. If you go to metals, it goes to selective laser melting, SLM, or direct metal laser sintering. Powder bed fusion is a common name to describe many of these variants. Here again, we will look at a brief description of the process, some attributes of the process and applications, and who makes these materials and machines. Let's start out with an overview of the process itself with this short video.
SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures.
More details can be found in this YouTube link that I've provided for you. So basically you have a bed of polymer powder spread layer by layer, and laser energy is used to fuse the particles. You can make high density complex shapes. Typically the mechanical properties you can get from SLS is greater in attributes than you can get with fuse deposition modeling. Because you have to use fine powder to be able to get good features, you have to be able to work with something that is very slow. The tolerances in surface finishes are limited, and any reinforcements of fibers that you add will be limited in terms of the L over D ratio of the fiber. And you saw during lecture 2 that the mechanical properties of fiber reinforced composites gets limited once you begin to reduce that L over D, which is necessary to be able to get fine enough powders. Typical applications include prototypes as well as tooling. EOS is one example of a vendor. Ricoh is another one. More recently, you have vendors such as Hewlett Packard, just like Ricoh, another 3D printing company, coming out of 2D printing expertise and market reach and just heavy reach.